Okay, so in this example, we're going to look at rewriting a radical function so that we can identify the transformations. So the question, how can you rewrite the following radical functions to identify their transformations from the parent graph of f of x equals the square root of x? So we are looking at our square root function. So this g of x equals the square root of 9x. So what we can do with this is we can say the square root of 9 times the square root of x, because that 9 is a perfect square, and we get 3 times the square root of x. How that helps us out is now we can see, oh, we have a vertical transformation. And it's going to be a vertical stretch by a factor of 3. There's no horizontal translation or vertical translation. We just have the vertical stretch. So let's plot the original parent function points. So in a square root function where we have 0, 0, then up 1 to the right 1, up 1 to the right 3, up 1 to the right 5. We're going to take those points and do a vertical stretch by a factor of 3. So how far away are they from the x-axis? It's 1, 2, and 3 units away. We're going to multiply those distances by 3 and plot our new points. So the distance that is 1 away, 1 times 3 is 3, so we're going to go up 3 on that same vertical line, 1, 2, 3. There's our new point. Now this next one is 2 away from the x-axis, so 2 times 3 is 6, so we're going to go up 6, 1, 2, 3, 4, 5, 6, and plot our point right there. Then the last one is 3 away, so we're going to multiply that distance by 3. We're going to go up 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we do that 0, 0 point did not stretch vertically at all, and we draw in our graph. All right, next example. H of x equals the square root of 4x plus 16 plus 7. So let's work on rewriting this. I see that this 4x plus 16 has a factor of 4 that we could factor out. So if we factor a 4 out, it leaves us with x plus 4, and then we've got our plus 7 on the end. And then we can take the square root of 4, square root of x plus 4, that plus 7 doesn't change on the end, and the square root of 4 is 2. We've got our x plus 4, and then plus 7. So what transformations do we have with our h of x function? We have a vertical stretch by a factor of 2. If that number was less than 1, between 0 and 1, we would have said a vertical compression. Let's see, we have x plus 4. That means we're shifting to the left 4 with that tricky x. And then that plus 7 on the end means we're going to shift up 7. Okay, so let's plot our parent function points. Here's 0, 0, up 1 to the right 1, up 1 to the right 3, up 1 to the right 5, 3, 4, there we go. So I'm just going to dot that one in. That's the parent function. So remember that 1, 3, 5 pattern applies just to our square roots because your square root function is tied to your x squared function. All right, we're going to do the vertical stretch first. So we're going to stretch these vertically by a factor of 2. So the distance away from the x-axis is going to double. So this point will be here. This point goes up that far, and this one is 3 away. So it goes up there. So here's our vertical stretch, and now we do our translation. Each point is going to shift to the left 4 and up 7 units. So starting with our origin, we go to the left 4, up 1, 2, 3, 4, 5, 6, 7. And what you could do is you can shift each point, or sometimes for me it's faster to say, oh, well, the next point is up 2 over 1, I've got my next point. So if I go up 2 over 1, I've got my next point. Then if we go up 2 over 3, that's going to be the next point. So I can go up 2 over 3 to get the next one, and then the last one won't fit on the graph because that last one didn't even fit on the graph, so we'll just call it good and sketch in our graph there. And there's our transformed graph.